Hello, I'm Mr. McChesney, and today we are looking at the force on a charged particle. So the problem we have is a beam of electrons travels at 3.0 times 10 to the 6 meters per second through a uniform magnetic field of 4.0 times 10 to the negative 2 Teslas at right angles to the field. How strong is the force acting on the electron? So here we have our situation drawn. We have the drawing where the magnetic field has little dots, and that represents a magnetic field coming out of the page towards you. The current, or velocity of the particles, is drawn at a right angle to that, and we want to figure out which direction is this force. So if you look back in your book, it talks about some right-hand rules, and the third right-hand rule is the one that applies here. So if you look at this, the magnetic field is coming towards you. So you put your fingers pointing towards you. Use your thumb to show the direction of the magnetic, or the direction of the charged particle, and your palm should be pointing downwards. So that's the direction of the force, except for we have an electron. And an electron is negative, so that flips the direction of the force. So instead of being downwards, it's going to be up towards the top of the page. So now that we know the direction of the force, we now want to know how to find it. So, as always, start with writing what you know. You know the velocity is 3.0 times 10 to the 6 meters per second. And we also know that the strength of our magnetic field, that's capital B, is 4.0 times 10 to the negative 2 Teslas. And we also know that the charge on an electron is negative 1, because it's an electron, negative 1.60 times 10 to the negative 19th coulombs. And what are we looking for? Well, we're looking for the force that acts on this particle. So if you look back in your book, to figure out the force, you need to know the charge of the particle, the speed of the particle, and how strong is the magnetic field that it's going through. So we're going to take our charge of our particle, negative 1.60 times 10 to the negative 19th coulombs. We're going to multiply that by the speed of our particle, 3.0 times 10 to the 6 meters per second. And then we're going to multiply that by the strength of my magnetic field, 4.0 times 10 to the negative 2 Teslas. So when you multiply all those together, you get a couple things. We get an answer that's negative 1.9 times 10 to the negative 14th. And it's a force, so it should be newtons. So let's check a couple things to make sure we did that right. So one, let's just take a look at our exponents. We had 10 to the negative 19th. And when you multiply exponents, you add the exponents together. So we got negative 19 plus 6 plus negative 2. So that's going to give us 10 to the negative 15th. So if we look, we've got 10 to the negative 14th, and it says we should be 10 to the negative 15th. Those are pretty close together, so that means that's a reasonable answer, depending on how the 1.60 times 3 times 4. So when we multiply those, 3 times 4 is 12. That means that would move our exponent over 1 closer to 0, so it would be negative 14. So that's a reasonable answer. And then our units, a Tesla is equal to a Newton divided by an ampere times a meter, and an ampere is equal to a coulomb per second. So if we substitute the ampere into the Tesla, we get a Newton times a second divided by a coulomb times a meter, and that, when that all is said and done, when we divide by our seconds and take it out, we get a Tesla. If we make everything on the sides equal, Tesla times a coulomb times a meter divided by a second, and that is equal to a Newton if we rearrange everything. So we've got here is our expression for newtons. We got a force that ends up in newtons. Our exponents check out. So negative 1.9 times 10 to the negative 14th newtons. It's negative because we've got a negative charge. And you remember from the right-hand rule, our fingers were coming out of the page. Our thumb points to the right. Our palm was down. The force should have been down if it was a positive particle, but it flips to the top